Thanks a lot, and thanks to the organizers of the seminar for inviting me. So I am a statistician postdoc Mendenhall at the Earthquake Science Center in Moffett Field, California. It's just my name on this title slide, but this is really collaborative research that I've been lucky to do with the operational aftershock forecasting team here at the Earthquake Science Center and other science centers. As well as other partner collaborators from different countries, which I'll come to shortly. And I'm proud that this work has been supported by the U.S. Agency for International Development through its Bureau for Humanitarian Assistance. So this talk will be all about aftershock forecasts. So I'm going to introduce the topic, and then I'll get into our social science research on identifying user needs for aftershock forecast products and improving our current products based on those user needs. But first, I wanted to give you a little more introduction on who you're going to spend the next hour with. So my training has been in statistics and mathematics, but I've been collaborating with earthquake and social scientists throughout my career. I cut my teeth in earthquake research, testing earthquake forecasts at the Collaboratory for the Study of Earthquake Predictability at the German Research Center for Geosciences in Potsdam, Germany. I then did my PhD in statistics at the University of Washington and had several impactful research stays at the Max Planck Institute for Human Development in Berlin. My research follows two different branches. So in statistical seismology, my doctoral work looked at the seismicity of the Pacific Northwest in order to model its aftershocks. This required merging multiple catalogs in the Pacific Northwest. So I got to know a little bit about network seismology that way, and I'm really grateful to my network colleagues for their support on that. We then went on to create Bayesian methods to estimate the parameters in state-of-the-art aftershock forecast models. Using Bayesian techniques for the sparse PNW that has a lot of complex structures in it. So we were able to study how these different tectonic regimes, these different swarms, affected the aftershock parameters in the PNW. And if you're interested in that kind of work, I encourage you to look at those papers, including one about to come out in BSSA. The second branch of my work focuses on visualizing these earthquake forecasts and using social science experiments to optimize that data visualization. So I've looked at how to best visualize uncertainty in aftershock forecast maps and how to choose colors and data classification for seismic hazard maps. So thinking of that as a long-term earthquake forecast. But all of our work today will stay in the short-term realm of aftershocks, which we know that large earthquakes will trigger additional earthquakes following them, and that these aftershocks complicate all of the work that has to happen after an earthquake, from urban search and rescue to the inspection of buildings to repairs and recovery efforts that take place over long spans of time. We know that aftershocks can compound the losses caused by a main shock. So an important example of this is in 2010 in New Zealand, there was a magnitude 7.1 main shock that led to an aftershock that was smaller in magnitude, but right near the major city of Christchurch, which killed hundreds of people. You can see in this top picture the cloud of dust that emerged over the central business district of Christchurch because of all of the collapsed buildings. Some aftershocks might even be larger in magnitude than their preceding earthquake. So the magnitude 9.1 Tohoku earthquake was preceded by an earthquake of magnitude 7.3. And another reason why aftershock sequences are impactful is that they can last for years following the main shock. So in 2020, Southwest Puerto Rico was hit by a string of earthquakes leading to a very productive aftershock sequence that has elevated the seismicity rate far above baseline even 5 years later. And this creates major challenges for the recovery and rebuilding efforts that have to happen following a disaster. So predicting the main shock itself is not possible by scientific means, But the aftershocks that it triggers follow patterns that are well known and that can be incorporated into a forecast model. And so these aftershock forecasts are important because they provide situational awareness to people who are doing all of this post-earthquake work, but they increase the overall resilience of an affected community by arming them with more information that can aid lots of decisions they have to make, like should I ride my bike the day after an earthquake, for example. And so government agencies have been releasing aftershock forecasts following large impactful earthquakes. The USGS is one of them, but GNS Science in New Zealand and the Italian National Institute for Geophysics and Volcanology communicate aftershock forecasts to different audiences using a variety of products. So those might be words or texts. These are numerical forecasts from numerical models, and so we can just show the numbers, we can graph them, we can map them. There's a lot of different kinds of forecast products that can come out of aftershock forecasts. Importantly, those products are then disseminated out by other groups. So this could include seismic networks, who are often asked questions about aftershocks and aftershock forecasts, but also emergency managers and other professionals, and ultimately by various public communicators, including the media. So before I talk more about aftershock forecasts, I just want to clear up some common terminology questions. Okay, so an aftershock is an earthquake that happens close in time to an earthquake of a larger magnitude. So in this image here, the first red earthquake triggered a number of smaller aftershocks. But then if an earthquake is triggered that is larger in magnitude, that gets retermed the main shock. And all of its subsequent earthquakes that follow closely in time are called its aftershocks. And all of the preceding earthquakes that happened beforehand are called foreshocks. But this is a question of terminology. These are all earthquakes. They can all damage our societies and our environments. And they can have any size following a magnitude distribution. And so importantly, we just have to keep in mind that earthquakes can be triggered, aftershocks can be triggered that are larger than those that happened before, in which case we would just reterm them main shock. Now, when I say forecast, I mean a very specific thing. I mean a statement about the probability of future earthquakes that is specified for a specific magnitude range for a specific window of time and for a specific spatial area. So a forecast says what might happen with an associated probability of occurrence and not what will happen. That would be a prediction statement, and that's the distinction between a forecast, which in our definition is probabilistic, and a deterministic prediction. Importantly, these forecasts should be updated as aftershocks occur and we learn more about the sequence. And that's because even though sequences follow some overall principles, sequences also vary in their dynamics and have to be modeled specifically. So what are those principles that I just alluded to? Well, a century of seismological study has found empirical laws that describe how aftershock sequences develop. So the first is that we know that more aftershocks are triggered by a main shock of a larger magnitude than that by a smaller magnitude. The larger the main shock magnitude, the more aftershocks are produced. When do those aftershocks take place? Well, we know that the rate of aftershocks decreases with time. So we expect a lot of aftershocks to be clustered soon after the main shock, and some, but fewer, to happen later on in time. We also know that the rate of aftershocks over space will decrease with distance from the epicenter, the main shock epicenter. So again, in much the same way, most of the aftershocks are expected to take place close to the main shock, and few, but still some, are expected to take place further away. How big should those aftershocks get? Well, we can expect many more aftershocks of a lower magnitude than of a higher magnitude, but aftershock magnitudes follow the same exponential magnitude distribution as main shock. So we do expect some that are higher. But importantly, the magnitudes of those aftershocks won't get smaller in time or with distance from the main shock. It's only the rates of aftershocks that decline with time and with distance. That means that even late in the sequence, larger aftershocks are possible, as we can see in this Northridge example. All right, so I'm now going to shift to our understanding of user needs for aftershock forecast products. So the USGS has had an operational aftershock forecasting system since 2018. We have been releasing public forecasts on the website, on our event pages for earthquakes above magnitude 5 in the US, and we just actually reduced that magnitude cutoff to magnitude 4. So in our US system, we forecast aftershock rates. So we forecast the number of aftershocks that are expected for specific time windows, so the next day, the next week, the next month, et cetera, for different magnitude cutoffs, and in a particular spatial area that is usually defined by the main shock magnitude. So this is in our domestic system for US and territories aftershock forecasts. We release tables like this. This is one of our products, and we've recently expanded to a graphical version of these kind of forecasted rates. But we could get one step further and use the forecasted rates as inputs into a ground motion prediction equation and actually map the ground shaking that's expected from all of those forecasted aftershocks. And so this map here shows the chance of strong shaking, MMI level 6 or above, for the region around the El Mayor 2010 earthquake, for the following week after the earthquake. And so we have another operational system that was developed in collaboration with the Bureau for Humanitarian Assistance for forecasting aftershocks following earthquakes outside the US. And this forecasted shaking map goes into that forecast report that goes out to our international partners. So aftershock forecasts present some communication challenges. For one, they're multidimensional, they're varying in space and time. They need to be updated as aftershocks occur, and so they change with time. And as you can see here, they span orders of magnitude in the expected values across different magnitude levels. So we have traditionally been using text-based products alone, and visual products could do a better job at communicating these aftershock forecasts, especially in situations where they need to be ingested rapidly for quick decisions. The issue is that doing this in an effective, visualizing our forecasts ineffectively could have an opposite effect, an opposite outcome. It could lead to the risk being misinterpreted and worse decisions getting made. So our guiding question here is, how would we design effective forecast products? And to make this question more user-centered, we're reframing it to ask how we design visual products around the needs of real users. So who are these users and what are they doing with these aftershock forecasts? So civil engineers, so we've studied this in the social science literature for over a decade now. And we know that civil engineers are using aftershock forecasts to inform how they inspect buildings or delay the inspection of buildings. Emergency managers use them to allocate limited resources across the affected area. Science communicators are using aftershock forecasts to deliver information about aftershock risk to larger audiences. And we know that network operators have used them to inform how they respond to media about the chances of more earthquakes. But this list goes much, much longer. And the reason I have use cases in red is because in our world, it's the use case. It's how someone is using an aftershock forecast that gives rise to user needs. And so this has also been studied to some degree in the literature, and it's been found that user needs should vary by profession, probably because different professions have different use cases. One thing that hasn't really been explored is how those user needs might vary in different countries. And we're often in a situation where we're communicating these forecasts across borders. So our guiding question in this research is how visual products can support the use cases that different professions have, and that might be different country by country. And so our roadmap to answering that question has 4 steps. We first gather the users together and ask them about their use cases and their user needs from aftershock forecasts. So we do this in stakeholder workshops, and the outputs of that go directly into designing new forecast products that are centered around the needs that these different users have. Okay, so then we have a whole suite of new products, and we want to test which ones are actually most effective. So we'll conduct an experiment where participants will do tasks with different forecast products. And those tasks will be based on the use cases that we learned about in the workshop. So that feeds into the experiment phase as well. And analyzing that experiment will then reveal how well those forecast products that were designed around user needs, how well they actually met them. So we're doing this whole research program with partners in Mexico and El Salvador. So we share a very seismically active border with Mexico and a larger geopolitical region that would with Mexico and El Salvador that might require communicating aftershock forecasts across these borders. And so these are the 3 countries in our study. And for the rest of the talk, I'm going to focus on these first 2 steps of this research program. So in 2023, we held stakeholder workshops in all 3 countries, working closely with our partners in Mexico and El Salvador, who are kind of equal partners on all of this research. We recruited 86 participants from about a dozen professions who are current or prospective users of aftershock forecasts. So this includes emergency managers at all levels of government, public health officials and other risk managers in urban planning and education fields, and firefighters and first response officials. So these are the public decision makers and on-the-ground people who would be using aftershock forecasts for life safety decisions. Then there are the more technical user groups, so different kinds of engineers, critical infrastructure operators, who would be using aftershock forecasts to inform the inspection and rebuilding of damaged infrastructure, roads, buildings, bridges, etc. And then we have folks who would be communicating the aftershock forecasts out to wider audiences and using them for other kinds of kind of information delivery tasks. So these are the target user groups in this study. So for each of our 3 workshops, we follow the same procedure. We first introduce the topic to our participants through non-technical reports and webinars. And that was so that we could ask them to brainstorm use cases before the workshop. So here, finally, I'll define what we mean by a use case. It's a decision in someone's line of work in earthquake response, recovery, or rebuilding that can be informed by an aftershock forecast. So that is a use case, and every participant came to the workshop armed with at least one use case. So then in the workshop, the main activities were these breakouts, where we split the participants first by profession, and we asked them to select one use case that represented their field. And then for that use case, for that decision that could be informed by a forecast, what information from the forecast is essential? Is it the number of forecasted aftershocks or the probability that one will be damaging? Is it the temporal or the spatial rates of aftershocks? Is it rates or is it the shaking caused by aftershocks? Then we ask them how that information should best be displayed, shared, presented to them in a product for that specific decision that they have to make. We then asked them to think about those two kinds of user needs, information and product needs, for right away after the main shock, 1 week later, and 1 month later to see how those user needs might change with time. So then we repeated the breakout activity, but now with groups that were mixed across professions. So we had a bunch of these mixed profession groups and we gave them all the same use case that was about resource allocation following the main shock. So we thought that was relevant across all these different professions that we had. And again, we asked them to come to consensus about what information from the forecast do you need to allocate resources in your line of work, and how should that information be turned into a product? And so you can see in these snapshots that the breakout groups reported back to us. We then had these facilitated discussions where we showed them candidate forecast products and asked them questions. It was a really interactive and productive trilogy of workshops, and we really learned a lot. So what did we learn? User needs definitely varied by profession and to a lesser degree by country, but there was one forecast product that was requested across lots of different user groups and countries. And that was a map showing the forecasted shaking from the future aftershocks in the following period. So technical users wanted this map, but they wanted it really detailed with as many colors as possible, showing maybe some additional information on geoscientific information on top of the forecast. So fault lines or the previous aftershocks that occurred or some other information to contextualize that forecast. Communicators and more of the qualitative users, they also wanted forecasted shaking maps, but they wanted them as simplified as possible with as few colors, maybe 2, maybe 3. They wanted also some compact summary of the spatial information somewhere in the product as well. So they wanted to be able to kind of see it at a glance and take the information forward. Some of them wanted the map animated as well, so maybe a more involved product, but they wanted to be able to see how the shaking was forecasted to decrease with time. So forecasted shaking was very popular. The information that we're putting out in the USGS forecast, which is about forecasted rates of aftershocks in different magnitude bins, that was also relevant to a number of use cases that came up. So geoscientists wanted that kind of information for planning temporary seismic networks to measure aftershocks. And emergency managers wanted to tell their teams on the ground about smaller aftershocks. And so the forecasted rates were useful for that kind of use case. Now, when we mix the groups across profession, we again got some pretty consistent request for a product that could be interactive, for an interactive dashboard that could show both the forecast map and other information beside it. Interactivity was key because it let users set their own thresholds on the forecasts, which might vary by users, but also by use cases, and set different durations or make choices about how they received the aftershock forecast info. They could also add map layers that could contextualize that forecast. So the main shake map was of interest, and every user had their own locations of interest corresponding to their use cases. Now, when we analyzed the user needs by country, we didn't find nearly as big of a difference. So one example of a difference is that in the US, there was more appetite to compare the forecast against background seismicity rates. And that might be because the participants in our US workshop were more familiar with earthquake information and products and had some exposure to the idea of a background seismicity rate. In Mexico, there was interest in comparing the forecasts with earlier aftershocks. And in El Salvador, there was a need to show the forecast in light of the previous damages that had come from the main shock or earlier earthquakes. In general, in Mexico and El Salvador, there was greater spotlight on comparing the forecast to other risk and vulnerability and exposure information. But in general, the differences were much larger by profession than they were by country. And we hypothesize that this is because the use cases across professions differ much, much more than they do across country. One other important factor in the user needs that were elicited was in the time since the main shock. So soon after the main shock, folks really wanted, across professions and countries, they wanted forecasts for shorter durations, maybe up to 3 days out. And there was this real primacy of the spatial information. People wanted the map first and foremost before any other kinds of information. But for some user groups, they really wanted that map as simplified as possible. Soon after the main shock, people also wanted a forecasted probability of some substantial aftershock, where that substantial could mean different things for different use cases. So that again belies the importance of an interactive forecast product. Later, after the main shock, so 1 week or 1 month later, there was a greater appetite for longer duration forecasts, so a week out up to a year out. And there was more interest in the kinds of magnitude binned products that we're releasing now in our forecast, as well as graphics that show the temporal evolution that's forecasted. Folks really wanted to see interactive systems, but only later on, some week or later after the main shock, insisting that it also propagate forecast updates. Now, color came up quite a bit in our workshop. There were different preferences for map colors and other products colors that varied by use case, and to a lesser degree by country. But that was through the different expectations and norms that different countries have for earthquake information. So for example, the USGS shake map colors are different from the shake map colors of the Mexican National Seismological Service. But across the board, reds were seen as useful for marking high-risk locations, and heat colors were requested across professions and across countries for showing different gradations of risk. One place where there was some difference in opinion was in whether the shaking forecast map should use the same colors as the shake map for the main shock. So some use cases needed a comparison between the forecast and the main shock shaking. Others didn't. And so there was a real split on whether the forecast map should use their own color palette. That's different. Another area of division was in which file format was requested. So some people preferred the portability and the ease of use of PDFs and other image files. Others really wanted KML and GIS layers for the maps to come out in that way. And others insisted on animations and GIF files. And so offering a variety of file formats is really important for meeting user needs. But as we've seen, there's a huge range of user needs that relate to the huge range of use cases. And rather than trying to satisfy every individual user need and use cases, we found in our analysis that there were some categories of use cases that could inform a product design strategy. So these are based on the information that's required out of the forecast in order to make the corresponding decision. So there's those decisions, those numerical decisions that require taking numbers off of the forecast product and doing calculations with them, setting thresholds, making models. So for example, a critical infrastructure operator might need the numbers from the forecast to do a cost-benefit analysis of where to prioritize their damage assessments of different roads or airports or other infrastructure. There's other decisions that don't need numbers. They just need to understand, where is the forecast higher or lower? When is the forecast higher or lower? For which magnitudes is it higher or lower? For example, a public health decision maker who needs to set up an emergency medical triage system, they might want to locate their triage points in relation to the forecast, but kind of just relative to where it's higher or where it's lower. And then there's a whole bunch of decisions that don't require numbers or comparisons because they just need the overall big picture of that forecast. So a geoscientist communicating aftershock risk to a media reporter in a 2-minute video segment, they might need just one main message to take from the forecast. But importantly, that geoscientist, in order to understand the forecast itself, they might need more of the numerical product type. And so what's key is understanding that a single user could require a suite of different products and to satisfy different use cases that they have for this information. Another key finding here from our workshops is that users really wanted additional support for understanding and using aftershock forecasts. So they wanted to establish partnerships with science agencies to train them before a big earthquake on understanding aftershocks and aftershock forecasts, and to co-develop thresholds that would relate to their operational purposes. During an aftershock sequence, science agencies could send liaisons to assist partner institutions in applying a forecast and making decisions that that institution needs to make. And there was a big appetite for automated decision support tools for aftershock forecasts that are customized to different user groups in different fields. So that would be another set of kind of user needs that we identified in this research. So in my last few minutes, I'm just going to show quickly how we have improved some of our forecast products based on these user needs. So we follow a simple procedure for this step of the research where we take a single product, so let's say a shaking forecast map, and we think about all of the design choices that one has in making that map. So what are the colors that you use? What are the ways that you split the forecast variable into different classes? How does a legend look? What about the titles and the captions? So these are all design parameters that can be separated out. And what we're trying to do is translate the catalog of user needs that we've identified in our workshops into choices for those design parameters. So there's going to be different prototypes made for a shaking forecast map or for a temporal graphic that could relate to the different sets of user needs that we identified. And so that results in a large set of draft prototypes, which we then revise based on internal feedback across our multinational project team and external feedback, where we share those revised prototypes back to the original workshop participants to see if we've hit the mark. And that's what gets us our final prototypes for user-centered aftershock forecast products. So let me just break this procedure down with an example. So again, this probability of strong shaking map, this is kind of our baseline version. It's got a lot of different design choices. So for the color palette, we chose this yellow to brown that goes through orange and red palette. We split the probability variable into 10 classes, and we chose those breakpoints based on our application for the Bureau of Humanitarian Assistance. This baseline map doesn't have any other map layers. It's got what I'm calling the standard map title and map caption that doesn't have any additional information, and it's made for a week duration. So those are the design parameters for this this product type. So what if we redesigned this map more aligned with the needs that we learned about in the workshop? So first, we could make the map for a shorter duration, let's say for the next day. We could simplify the map. So this is probably the number one thing we heard across the workshops is these products should be simpler. And so here we've reclassed this probability variable to have fewer colors. We've also removed some of the city labels and other kind of extraneous information to reduce down the information on the map. From one of the user groups, we were specifically asked to use shades of red to signify risk on these maps. And so we tried to create a color palette for that. We added some worst case scenario information. So these are the compact summaries that were requested. So here we took the maximum value from this probability map and put that directly in the map title. And we made the relevant dates for this forecast explicit so that people don't have to search somewhere else for that information. We also added another layer on top of the forecast map showing the previous aftershock scaled by magnitude and the main shock with a gold star. And so this is just one prototype that we could use to satisfy the needs of some of our users. But as I mentioned, there's a lot of different needs, and some of them really conflict with each other. So we've gone one step forward, and working with our student collaborator, Bianca Artigas, we designed this user-centered interactive viewer for the forecasted shaking maps, where users can select a color scheme. They can select the level of detail. This is how many classes that color scheme is divided into. They can select map layers. They can select to see the forecast at different time points and go back and forth over time to kind of animate the forecast over time. We've added some interactive capabilities where they can click on a point or hover over the map to get the actual values for those who need numerical values more precisely. And we've let users download the forecast map as a PDF. We've since added KML, and we're still fine-tuning this viewer based on user needs and reflections. So where we are now in this research is in finalizing all these different prototypes for different forecast products, maps, temporal graphics, magnitude bin products, interactive products. Ask me if you're interested also about the video games that we're developing. So lots of different product types. We collected the external feedback from our workshop participants in an online focus group, and we're working on final prototypes now. And then we'll test these in our task-based experiment. So again, the participants here will be members of target professions from all 3 countries. And we'll ask them to take one or several of these prototypes and do tasks that are based on the use cases that they told us about. And the responses to those tasks will reveal the effect that a product has on meeting a given set of user needs across professions, across countries, and their interactions. And so when I talked at the beginning of this presentation about effective forecast products, I mean that they should have the desired effect. And so this experiment is one way of measuring the kind of effect that a product has in meeting user needs. Finally, this will inform products that we can use at USGS for our OAFs and in other countries. And I'll just plug quickly that we've had really productive collaborations with our partners in Mexico and El Salvador who've used our forecasting software and products in their own countries. And so this is having impact outside of the US as well. So that's it for me. I think I went a little bit below time, but I hope we have more time then for questions.